So welcome back. In this second part of the session, we will first have two presentations from the two Chinese projects to build space-based gravitational wave detectors, Tianqin and Taiji. And it is my great pleasure and honor to welcome Luo Jun, Professor Luo Jun, who is an old colleague and a good friend. And he has built the Center for Gravitational Wave Research in Wuhan, which is now the largest center in the world. And then he went on to become the president of the Zhongshan Daxue, Sun Yat-sen University, one of the biggest universities in China. And there he has built the Tianqin Center in Zhuhai, which is a huge, huge center. And now he's not president anymore, I believe, but back full power in Tianjin, I hope. So please.
Yeah, dear Gerhard, dear friend. First of all, I would like to thank the organizer for giving me a chance to introduce our Tianqin project. This is a plan of my talk. Since the first detection of gravitational wave by LIGO, we have iterated the area of using gravitational wave to detect the universe. However, gravitational wave detection is still in its infancy. Most gravitational wave signals and the most part of universe are still out of reach, and many gravitational wave related questions still lack answers. By looking at the spectrum of gravitational waves, one can see that the mini-Hertz sector has the most diverse gravitational wave sources, most diverse distribution of gravitational wave sources in the universe, and the highest detection precision expected, and so is the golden frequency band of gravitational wave detection. To effectively detect the gravitational wave with mini-Hertz frequencies, one needs to use laser interferometer with luminance at the scale of 100,000 kilometers, and so the detectors must be formed in space. That is, by doing space-based gravitational wave detection. Tianqin is one of several space-based gravitational wave detectors. On this slide, you can see the sun, the yellow ball in the middle of the picture. To the left, you will see the Earth, which is blue. Surrounding the Earth, there are three dots marked as spacecraft 1, 2, 3, which form the constellation of Tianqin. When the Tianqin was originally proposed, no one knew when the gravitational wave could be first detected. So the orbital plane of Tianqin had been chosen to face the ultra-compact white dwarf barrier 00806 to maximize the response of Tianqin to this particular source and to let Tianqin detect gravitational waves as soon as possible after its launch. Since the orbital plane is nearly vertical to the ecliptic plane, it looks like a harp in space, and so is the meaning of Tianqin in Chinese. Since Tianqin is using geocentric orbit with a radius of about 100,000 kilometers, its sensitive frequency bands is in the between those of LISA and DISEGO. The detector is also expected to be easy to deploy, track, control, and to communicate with. If everything goes smooth, we expect to launch Tianqin around 2035. Our team started gravitational experiment in early 1980s. In 2000 and 2000, we started to do research on two technologies of space-based gravitational wave detection, inertial sensor, and intersatellite laser interferometry. In 2030, the electric static inertial sensor was the first successful test in orbit in China. The Tianqin project was officially proposed in 2014. Since 2016, because of the breakthrough made by LIGO, there has been a lot of attention come to gravitational wave detection. Tianqin project has also picked up momentum. During the past few years, we have carried out 2 major projects in the technology roadmap of the project and have reached important milestones. We expect to reach another milestone in the next 5 years, so-called Tianqin 2 second. On the right one, you can see many types of sources that can be detected by Tianqin. One can notice an important feature here. For different types of sources, the range of detection is different. With such diverse type of sources, one can expect Tianqin to make a huge impact on science in areas including fundamental physics, astrophysics, and cosmology. In the following, I will discuss some issues that have been considered challenges in the mission concept of Tianqin. First, Tianqin will be operating in a complicated gravity field environment. On the left, one can see an illustration of Tianqin in the solar system. Note, the objects are not drawn up to scale. Before Tianqin, no one has tried to use a constellation whose orbit plane is vertical to the eclipse. The presumption was that no stable orbits can be found in such configuration. Through simulations, we have found that not only there exist highly stable orbits, but there are many of them. We are lucky. The key to the solution is that the factor of moon can be minimized when the orbits are vertical to the lunar orbit. Earth is not a perfect sphere, as one may usually assume. In fact, there are significant irregular distribution of mass on Earth, which lead to an irregular distribution to the Earth's gravity field. So, when the Tianqin satellites orbit around the Earth, they are moving in the irregular gravitational field, which can lead to irregular relative motion between the pairs of satellites. Such added irregular motion could interfere with the gravitational wave signals. With a high precision numerical simulation, we have found that there is indeed significant contribution to the acceleration noise expected for the test masses. But fortunately, the Earth's cause acceleration noise decreased steeply around 10 to -4 Hz. It's below the requirement of Tianqin, above 10 to -4 Hz. This means the acceleration noise induced by the Earth's gravity field will not be a fundamental obstacle to Tianqin. The moon can get in between the sun and the Earth every month. And so there is a significant chance for moon eclipse. Moon eclipses could cause fast and large variations of sunshine on the satellites, and the result, the thermal shock, could cause interruptions to the gravitational wave detection. So it is an issue that one should worry about. We find that by using moon resonant orbits, it is possible to have stable orbits that experience no moon eclipse during the observation times, for example, 5 years. The earliest known challenge issue concerned Tianqin is the sun radiation. Due to its unique configuration, the orbital plane of Tianqin is nearly fixed in the space, so the sun will involve a round constellation and passes through the orbital plane of Tianqin every half years. The large variation of the angle of solar radiation is making the thermal environment complicated and challenging. We have recently found that within the detection band of Tianqin, the radiation noise is dominated by the solar constant fluctuation. Of course, this does not mean the problem has been solved. We still need to find a way to deal with the long-term variation of the radiation flux. But now we can mainly focus on the latter problem. A second potentially important challenge for the Tianqin is a solar wind plasma. Due to the long distance in intersatellite laser propagation, there is a danger that the space plasma could become a significant source of phase noise. That is quite different from LISA. Our preliminary studies show that plasma-induced phase noise is sub-dominant except during the strong magnetic storms. But some study is needed to minimize the potential impact of the space plasma. To sum up this part, several of issues that have been raised as potential problems for Tianqin have been shown to be not difficult to solve. There are still issues like sun radiation and the solar wind plasma. One must study them seriously. Apart from the challenge mentioned so far, the most important challenge comes from technology. In the following, I introduce very briefly the progress we have made with the technology development. To successfully detect a gravitational wave in space, we need to accomplish several key technologies, which I am sure many are familiar with now. We have adopted that 0123 technology roadmap to bring the required technology to maturity. For this, we have planned a few major intermediate projects. Starting from 2016, we have made some important progress with this roadmap. Tianqin satellites are using the geocentric orbit and are not too far from the Earth, so it is possible to use laser range technology to help obtain high precision orbit information, which is helpful in mission scheduling and in data analysis. Because Tianqin is not there yet, we started by doing lunar laser range. Apart from its application in the Tianqin project, lunar laser range is also significantly important in studying the Earth-Moon system and in testing general relativity. Our lunar laser range project officially started in 2016 when it received funds and support from China's National Space Agency and the National Science Foundation of China. Our new laser range station was complete in early 2019, and on June 8, 2019, we carried out the first successful range experiment to the moon. On November 7th, 2019, our new station successfully ranged to all 5 natural reflectors on the moon. A preliminary analysis show that statistical errors in most of normal points are better than 1 centimeter.
Roger, we still have 5 minutes, including discussion.
Yeah, okay. In the second mission in the roadmap is a Tianqin-1 experiment satellites. The goal of satellites to test the 6 keen technology in orbit. On December 20, 2000, the satellites have launched and it accomplished on January 21st, 2021. The experiment on the satellites can be roughly divided in 4 planes. Apart from testing the technology of Tianqin first have also collected data and enrolled the first interface on Earth's gravity field. As a short summary, we have get a fruitful result for the Tianqin-1 satellites. The third mission in the roadmap is a Tianqin second experiment satellites, which will be launched around 2026. To support the research of Tianqin, some indicated research facilities have also been built, include the Tianqin Center, Tianqin Laser Range Station, and a cave laboratory and the ground simulation facility. Since the start of Tianqin project, there have been many international experts contributed to the project through many different ways. Here, I would like to express my thanks for all of them. Finally, let us talk about the future plan and the time schedule for the project. During the past years, we have been quite successful having the next research facility in place and in carrying out 2 major milestones. And our Tianqin second will be launched in expected to launch in 2026. After that, we expect the final mission for the Tianqin detector will be officially approved and expected to launch the detector around 2035. Thank you everybody.
Thank you very much. This is truly impressive. There are many technical details that one could discuss for days and not only in 15 minutes. The time is too short. I'm really looking forward for something like a Tianjin Symposium, if that's possible, maybe online, even better in China, but right now it's difficult to travel. But there are many technical things really interesting to discuss. Do we have any particular questions? What is the constellation breathing angle for Tianjin?
Thank you. I hope to have a chance to hold a meeting offline and invite all of you to visit Zhuhai here. We have already the meeting online already, but I hope in the near future.
Yeah, the breathing angle is shown here. It looks smaller, 10 times smaller than these are.
Yeah.
And Olaf,
this object is more stable because it's very close to our Earth. I think I don't know the exact the result because our college have numerical simulation about that. What is?
There are 3 more technical questions, but maybe you can discuss them offline. We have to move on to the second presentation by Walter Ren, whom we also know very well. He was a postdoc in Hanover, and he's now in the TaiG project. Please.
We can't hear him.
No, we can see your screen, Walter Ren, but we cannot hear you.
Now can you hear me?
Yes,
Yes.
very well.
Can you hear me?
Yes,
Can you hear me?
yes, yes, yes.
Okay, great. So this is the outline of my talk because I guess everybody heard a lot about the science and the significance of spaceborne detection. So I will skip this and go directly to the TaiG program. And okay, as everybody knows that there are 2 missions in China. One is Tianqin and Professor Lin. I really give a wonderful talk on that. So I'm going to talk a little bit about TaiG. So TaiG consists of 3 satellites, takes the heliocentric orbit, and the R1 is 3 million kilometers. And this project is led by the Chinese Academy of Science. And here is the little brief history of TaiG. TaiG is initiated by Professor Huang Rui on 2008. After a few years feasibility study, and we obtained a preliminary mission design. And after a few years of technology development, we launched TaiG-1 on 2019. And I will talk a little bit more later. So we keep on the development, and I will tell you the progress. Okay, here is the science. TaiG has 2 types of primary sources. The first is the intermediate and the supermassive black hole measure, and the second is the intermediate and the extreme mass ratio inspiral. And other sources such as the galactic binary and primary stochastic background, and I will not go into detail here. The science is very promising, but the technology is quite challenging. The first is the so-called inter-satellite laser interferometer, and we needed to reach 1 picometer displacement measurement over millions of kilometers. And the second is drag-free control. We needed to realize super fatal G free falling for the test mass, which is already achieved by Lisa Pathfinder. So that's why we take 3 steps to realize the final goal. The first is to test the technology on ground, and it contains all includes the TaiG-1 mission. And the second step is to launch the TaiG Pathfinder, also named TaiG-2, to verify all the technology for TaiG. And step 3 is we hopefully can launch TaiG maybe a few years after 2030. And this is TaiG-1, and it was adopted on 2018 August, and it was launched just 1 year later. So it's very quick mission, and we test quite a lot on this satellite. You can see here is the interferometer and the sensor head of the accelerometer. And we install 2 types of iron thruster. One is RIT and the other is Hall. We install 2 lasers just in case, and they both work well on the orbit. And this is the electronics for the sensor, and here is the phase meter. And if you want to look at the detail, please refer to this article. So I will talk a little bit more about TAIJI2 and its progress. And what is TAIJI2? Okay, because TAIJI1 is relatively simple, so we need a mission to bridge the TAIJI1 and 3. TAIJI2 is actually one arm of TAIJI3. It consists of 2 satellites. One is master satellite. And okay, so there is one set of measurement system. It contains one inertial sensor, interferometer, and telescope. And for the master satellite, we replace one set of this measurement system to the fiber interferometer to simulate another arm, which we can use to verify the TDI algorithm. For the other satellite, we call the slave satellite. Just to save some money, we replace this set of measurement system with dummy mass. If we have enough money, we may wanted to install another inertial sensor here on the master satellite. So this is a glance of the TAIJI2 satellite constellation. It takes a heliocentric orbit, trailing Earth a little bit about 2 or 10 degrees, depends on the money. And the arm length is 1 million kilometers. So the interferometer developed for the TAIJI2, and we use the optical bond. We build 2 one-to-one model of the interferometer, and we build the link, and they can interfere with each other. And we also test this in the vacuum chamber. This is the phase meter, and the number is quite nice. They can reach 6 picometers, less than 6 picometers. Here is the laser with the fiber amplifier, and this is the FP cavity to stable the frequency of the laser, and we can obtain maximum 4 watts output power of this laser. And here is the primary mirror of the telescope, and it's a small scale. It's only about 100 millimeter, and it's well polished. The flatness is about 1/100 lambda. And here is the structure of the telescope, and we measured it. The stability is below 10 picometers. It's not that good, but it's enough for TAIJI2. And here, this structure is made of invar steel. We built another made of silicon carbide. They are quite similar. And here we also doing a experimental demonstration for the acceleration tracking and pointing for TAIJI2. For the acceleration, we use a camera, and we use differential wavefront sensing for the pointing. And the scanning pattern is Archimedes spiral. The precision of the acceleration is quite nice, but the pointing is not so good because maybe we are doing this experiment in the air. And we also made 2 of the pointing ahead angle mechanism. One is 1-dimensional, just fun, a toy model, and we're going to use a 2-dimensional PM for TAIJI2. And the longitudinal noise is quite essential for TAIJI2, so we measured it. This is the measure setup, and the number is 8 picometers per screw hertz. Not very good, but all right, it's enough for TAIJI2. We also made a prototype of the test mass. It's made of gold and platinum alloy, and this is the cage for the test mass. And we use the quantum machine to measure the parallelism and perpendicularity. And the number gives quite a nice meets even TAIJI3's requirement. This slide is the electrode for the electronics of the inertial sensor for TAIJI2. And we connect with the sensor head and test the displacement readout, and then the noise is below 1.5 7 nanometer per square hertz. And the driving voltage for the actuation, the fluctuation is below 3 pm, and these numbers are quite nice. So for the drag furnace thruster, and because we already flexed the iron thrust with Taiji 1 and the wet fine, so here we only focus on the thruster head, and here is the electronics. We build a pendulum to test the noise of the thruster, and this could get thrust just flew yesterday, and finger crossed, we hope it will bring us very good data. And we build a so-called quasi-physical simulator for the drag-free control. We actually see all the box. It has the same electrical interface same as the Taiji 2, and also the same data flow as the Taiji 2. And we simulated the whole process, including the acquisition, such as the scanning pattern. Here scanning and communication and acquired. And we turn the DWS on different reference sensing, so we can the curve become very narrow. And here is we release the test mass, and here we catch the test mass. And now we enter in the science mode, and it's work very nice. So we'll also build a toy model for the satellite, actually just to testify the structure, which we will install this measurement system on this structure. This structure is made of carbon fiber ceramics, and we experimentally measure the coefficient of thermal expansion, and the number gives quite a nice result. The platform, one of the key technology is the thermal control, and we made a thermometer, and the rate of noise is below 30 microkelvin along the interesting band. And we build a small box trying to see how can we control the temperature fluctuation. And here is the heater, and we put the thermometer in, and using the active and passive control, we tested this in a very huge tank, and we can see inside the box the fluctuation is very stable below 30 microkelvin. Okay, this is the positioning stage for the dummy mass, which is used to compensate the gravitational stiffness and also actuate the center mass of the satellite. And the positioning precision is quite nice. It's below 0.1 millimeter. Is good enough for Taiji 2. We also build a full link modeling, which we call the Taiji simulator. Is a numerical simulator, and it's a very nice platform which we can insert independent module such as the payload and the noise model and etc. And we can use this simulator to fine-tune the emission parameter, trying to find one optimized curve, and trying to maximize the science. And for the data analysis, we already have a GDI numerical simulator, which contains the random noise code ranging and also the frequency noise separation and the noise model. I mean, subtract the noise from the data pre-processing. For the science data analysis, we are about to release the first round mock Taiji data challenging, and the data set will be released maybe in the recent 1 or 2 months. So finally, the outlooks, we try very hard to catch up with the step of LISA in order to share 1 or 2 years flight time with LISA and trying to build the LISA Taiji network, which has a lot of very interesting science. Especially we can localize the source in a very precise manner. And a lot of scientists already work on this, and I'm looking forward more to come. That's all my talk. Thank you very much.
Thank you very much, Dr. Ren. That was very impressive. It's really fantastic to see so much progress, and indeed, it would be fantastic to have a Chinese detector at the same time with LISA. That will indeed open a complete new window of science. Do we have any questions? Maybe I have one. You showed a lot of hardware already. How many institutes of the Academy of Science are contributing to the hardware?
Okay, till now, we have more than 30 university and institutes contributed to all the hardwares.
Mm-hmm. Are they in one place, or are they all over the country?
All over the country.
Antoine asks, you mentioned the mock Taiji data challenge. How do you plan to organize it?
Okay, we are actually now, just planning or organizing this challenging, and we prepare already the data, and we now ask one of the group to do the data digging, try to dig out the sources and see whether this data, whether this scheme will work or not. So we wanted to release this data on public, and every group around the whole world can to attend the challenge.
Thank you.
Okay, thank you.
Do you plan to have some international symposium or conference or workshop or something like that?
Yeah, after the COVID things, maybe in maybe next year, and I will ask Professor Liang and see how can he organize one of the international symposium.
Martin Henry asks, in addition to the prospect of overlap in operation time with LISA, can you say some more about the expected overlap in frequency?
Okay, I guess the frequency is very much overlapped, almost the same sensitive frequency band, because we share almost the same arm length. Taiji has 3 millions of kilometers, and LISA has 2.5. So the sensitivity curve is very much overlapped.
Okay, thank you.
Okay, thank you all.
Well, thank you very much, Lojun and Ren. It was very encouraging to see, and I wish you the very best for your project and hope to see you more closely soon again.
Yeah, sure.
Here's one more question. What are the RPO and maintenance plan? But I don't know what RPO is.
Sorry, I don't know what is RPO.
Well, then we can move on to the next presentation by Waldemar Martens from ESA about another concept for space-based gravitational wave detection in the future, please.
Okay. Let me see. Can you hear me and see my screen?
We can hear you. And now we can also see your screen.
Let's see. Okay. Yeah, hello everybody. My name is Waldemar Martens. I'm a member of the LISA study team at ESA and as an orbital mechanics specialist. And today I would like to talk to you about a proposal for a successor mission for LISA called LISA MAX. And this is work done together with my colleague Michael Kahn and Jean-Baptiste Bale. So first, to give you some context, ESA is currently looking into potential future science missions which come after the Cosmic Vision program, which LISA is part of. And that is called Voyage 2050. You've probably heard of it, and covers the time frame 2035 to 2050. And among the themes that have been selected is also gravitational waves, and that has triggered, of course, some more interest and study of potential future mission concepts. In general, if you look at proposals for space-based gravitational wave observatories or projects, they use very similar concept from the orbital mechanics point of view. They always or mostly use triangular constellations using the Lagrange points or using Earth-like orbits or Earth orbits, as we have heard before in the presentations. And they target either a higher sensitivity or new frequency band. And I would like to in particular point out this one proposal, which is a white paper which was submitted to the Voyage 2050 call, which is probably the most similar concept to what I will talk about today by these authors here. So LISA MAX is trying to answer the question, by how much can we actually increase the constellation, so targeting lower frequencies and still be affordable? And the first idea was to use the Sun-Earth Lagrange points 3, 4, 5 and to place constellation there. So just as a reminder, every three-body system like the Sun and the Earth have these Lagrange points which are stable, fixed points, which means that the forces cancel out there. And it's very convenient that the points 3, 4, and 5 form an equilateral triangle, and would of course be a very nice place to put a constellation there. And such a constellation would have an arm length of 259 million kilometers, which is 100 times more than LISA. There's one problem with that. If you place a satellite in L3, seen from Earth, that's right behind the Sun, so you cannot communicate with it directly. You would have to use another satellite as a relay, but that would increase the mission complexity. We chose a slightly simpler solution. We just offset the whole constellation by 10 degrees. To move that satellite away from the Sun, you won't be in the Lagrange point exactly, but the disturbances at this place is still low enough, as we will see. So what you see here is already the fully optimized constellation, which means that the initial states, the position and velocities, have been finely tuned numerically to minimize the breathing of the constellation. So the breathing is the variation of the corner angles and the arm length rate over the mission duration of 10 years, assumed here. And as a reminder, so the corner angles need to be small because the larger the variation of the corner angles, the more the motors need to move to point to the distant spacecraft. And the requirement for the arm length rate comes from the bandwidth limitation of the phase meter. So if the relative velocity is too high between the spacecraft, it will induce Doppler shifts that move the beat node frequency outside the allowed band, which is for LISA between 5 megahertz and 25 megahertz in absolute value. And what we have achieved here, or what can be achieved here for LISA MAX, is much better than what we have for LISA. For LISA, we have typically corner angle variations of ±1 degree and rates of ±10 meters per second. And here we have an improvement of a factor of 10. The corner angles and a factor of 2 for the arm length rates. So such a constellation is really stable, and from the orbit mechanics point of view, it's a good place to put a detector there. of course, we're interested what a sensitivity curve would look like for such a detector. And for that, we need to take a couple of assumptions, which I've summarized here to compute the sensitivity curve. In particular, I want to point to two parameters, which is the laser power and the telescope diameter. The laser power, I've assumed the same as for LISA, 1 watt, although I'm sure that could be increased. For the telescope diameter, if you have an arm length 100 times larger than LISA, then you need to make up for the lower photon density, which is much lower, of course, at that distance. So to fully compensate that, you would need to scale up the telescope by a factor of 10, 3 meters, which is quite large and quite heavy, probably. So for now, we assume a 1 meter telescope, which is probably still large, and it's actually a driver, I think, for this mission concept, the mass of the telescope. So if you look at the sensitivity curve computed in a very simple model for both LISA and LISA Max, you see that there's a reduction of 2 orders of magnitude in the sensitivity. And because I talked before about the laser power and the telescope diameter, so those determine the laser shot noise, and that determines how high or low this point here, this minimum, is actually. So if we increased the telescope diameter or the laser power, that would move us further down here. And actually, the telescope diameter enters to the 4th power, whereas the laser power only enters with the 1st power. So the telescope size has a much stronger impact, but it also has a much stronger impact on the mass of the spacecraft. So, so with the assumptions taken, we're roughly at the same level as LISA here. And I want to point out that these are sky-averaged sensitivity curves, but LISA Max is bound to the ecliptic. So the constellation normal is always pointing to the ecliptic pole, whereas for LISA we have this cartwheel constellation where the constellation normal is inclined by 60 degrees, and during the course of a year, as the constellation moves around the sun, also the normal moves around the sun. So we get to see different portions of the sky during the course of a year, which we don't have here. Okay, we also looked briefly at different gravitational wave sources, massive black hole binary inspirals. So here you can see the traces that are produced by 2 different masses of black hole binaries, 10 to the 5 solar mass and 10 to the 8 solar masses, during a 4-year mission, which are fully in the LISA band. But if you go to a time much before the merger, 1,000 years or 10,000 years, you see it's no longer in the LISA band, but still in the band of LISA Max. So it's similar what happens between LISA and ground-based detectors, so that the signal goes from one band to the other. And there are surely many more science cases that could be investigated here, but for that I would point you again to the white paper by these authors that have a more clear or more detailed survey of the science case. The next thing that we're interested in is how much mass could we actually bring to this place, to this, to such a constellation? Because I mentioned probably we need large telescopes, and that means we need probably not a joint launch, but dedicated launches for each satellite. So for LISA, we have a joint launch. All 3 satellites are launched on the same rocket. So the final mass, the dry mass of the spacecraft, is a function of 2 things: how much mass can the launcher bring into orbit, and how much fuel do we spend during the transfer. And so that's what we do. We compute the transfer. And what we assume is that we have an Ariane 6-4 rocket, and that it can give us 10 tons at an escape velocity of 1 kilometer per second. So that is very well within the planned capabilities of Ariane 6-4. Probably we will have even more. And by the time we're looking here, probably even higher mass are achievable. So that's a conservative assumption here. But yeah. So the way this transfer works is that either we insert from Earth into a heliocentric orbit with a semi-major axis below the Earth. That will induce a drift. So because the orbital period of the spacecraft is lower, we will drift ahead of the Earth. So this green curve here. And then we drift as long as we, when we reach our destination, we fire our engines, do a braking maneuver and stop there. And the same, if we want to go into the other direction, we insert into semi-major axis higher than the Earth and drift and do a stop maneuver when we end at our destination. Of course, the braking maneuver, the size of the braking maneuver, and thus the fuel that you spend depends on how fast you go, how many revolutions you do around the sun. So in this plot, you see one revolution around the sun is one of these hops, because this is a rotating frame, right? So the Earth and the sun are always on the x-axis. So one such hop is actually a revolution around the sun. And we found that a good trade-off is like for the two spacecraft that go to L4 and L5 to do one revolution, almost 2 revolutions, and for the other one, almost 4 revolutions. Let's then look at the numbers. So what you see here on the left is the transfer delta V and the arrival mass. So the arrival mass is the function of the transfer delta V and the 10 tons launcher performance that I mentioned earlier. And they're different for the 3 spacecraft, of course, because they take a different course. And they also depend on the launch date because of the Earth eccentricity. So depending where on the Earth orbit we depart, we will have to take a slightly different journey, and that impacts the delta V. And since we want to build all our spacecraft, all the 3 spacecraft identically, what really counts is the minimum here. So between the 3 spacecraft, the minimum mass that can be achieved, and also if we want an all-year launch opportunity, also the minimum over the whole year. And this is like 6.5 tons roughly what we achieve here, with a 10 tons insertion mass. So that's about 3 times the mass of the LISA spacecraft, which is not surprising since we have 3 launches here and LISA has 1 launch and the delta V is very similar. Okay, I want to briefly mention, in the beginning I said that LISA Max is kind of driven by the question, how large can we constellation be while still being affordable? And so I want to briefly look at variations of this concept and see how that would impact the complexity of the mission and the mission cost. So one drawback of this concept is that we are bound to the ecliptic plane. And so the antenna pattern is fixed, although it rotates around the sun during the course of the year, the plane is always fixed.
Your slide is not updating. You still have the transfer cost on the screen.
Yes. Yeah, I have no slide on that actually. Okay. I'm just trying to. Yeah, so it would be actually nice to have a out of ecliptic constellation, but to achieve that, we would actually need a much higher delta V. So just imagine the velocity of the Earth is 30 kilometers per second on its orbit. If you want to significantly change that velocity, you need delta V's of the order of many kilometers per second, so much higher than here. So this is completely infeasible to achieve out of ecliptic constellation just with propulsive maneuvers. What could be done is similar to what is done for the Solar Orbiter mission. So that mission uses combined flybys between Earth and Venus to increase the inclination with respect to the ecliptic to observe the sun from the poles essentially. And a similar concept could of course be done here, but again, this increases the complexity because it's a much more complex trajectory, much longer, much more expensive operations and so on. So yeah, another option that could be considered to go beyond the Earth or the Earth-like orbit, like for instance to a Mars-like orbit, and put spacecraft in the Lagrange points there, for instance. But again, this has large impact on the mission complexity because the delta V is again much higher. You're essentially looking at 3 Mars missions there. Yeah, so it is feasible, but it has a large impact on the cost. So that's why I try to argue that kind of this concept is the maximum constellation that we can achieve while still being more or less affordable. Okay, just quickly on the transfer duration. Yeah, so with the transfer that we chose, we have 2 years for the 2 spacecraft that go to L4 and L5, and 4.5 years transfer. So the one that goes almost behind the sun. Okay, to conclude, yeah, so I've presented Lisa Maxwell observatory proposal, which lowers the sensitivity by 2 orders of magnitude, so makes it much more sensitive in the microhertz band. The main benefits, of course, that it opens a new band for gravitational wave observations. Compared to LISA, the constellation is more stable. So we have lighter requirements on the optical assembly and tracking mechanism, so the one that's sensitive for the breathing angles, and also lighter requirements for the frequency planning. The main challenges are that we probably need a much larger telescope and higher instrument mass. So if the telescope is a factor of 3 larger, the mass is probably a factor of 10 or so. We therefore might need 3 dedicated launches, which translates into higher cost. The constellation acquisition will be also much more complex, because to find a spacecraft that is 100 times further away than in LISA, you need to know exactly where it is. We have no omnidirectional sky coverage due to the fixed constellation plane. And okay, things that could be looked at in the future: how can we make the telescope smaller or lighter, and maybe bring them to a joint launch to reduce mission cost, and maybe increase the laser power, which could partly compensate for a smaller telescope. Okay, that's it from my side. Thank you.
Thank you very much. That's very interesting. Do we have questions? I don't see any yet.
Here, a hand by Stefano.
Yes, Stefano, yes.
Hi, nice talk, interesting. Actually, we are thinking to this thing very actively in the context of the follow-up on Voyage to 2050. I'd like to ask one thing. Below 10 to the minus 4 hertz, the acceleration noise we have measured in LISA Pathfinder goes up quite rapidly.
Yeah.
And we also have a hint that below, say, 20 microhertz steps up even more fast due to temperature fluctuation. How much this will spoil your science case?
Yeah, I mean, this is something, as I said, this is a very simple model. It has an impact on both curves, right? Because also the LISA curve doesn't take that into account here. We have just a constant acceleration noise here. But yeah, this will go up steeper, as you say.
Yeah. And at high frequency, what about the confusion noise? Due to the binary in the galaxy.
Yeah, I guess there are people who can answer that better than I can. I don't know.
Never mind. Thank you. Very interesting. Thank you.
Stefano has already asked Guido's question. More questions? Well, maybe one from me. I'm sure you are perfectly aware of that. There are other noise sources you have to consider which also scale with the arm lengths, like laser frequency noise, laser intensity noise, and many others. So what is the plan to, and you also know there are tools, tables, and simulators, for example, from Simon Bartel. So do you plan to refine the noise model? Or certainly you do, but any concrete plan?
We have no concrete plans. I mean, it would be, the first step would be to see how this concept actually compares with different proposals and see whether it's worth studying, because currently it's not an official either activity. It's just done essentially in our free time. So yeah, if there's more interest, then certainly we can, I think, especially with Jean-Baptiste and the software that, the simulation software that they have, it would be no problem to increase the fidelity of those noise models.
Jean-Baptiste answers the galactic confusion question. It probably does limit the sensitivity gain, but more binaries will also be resolved than in LISA.
Mm-hmm. Why is that? The frequency resolution is, well, never mind.
Maybe also the data analysis techniques will have progressed a lot by then. Okay, thank you. Then we are perfectly in time for the final talk of this session. Is about another technique to detect microhertz gravitational waves from Alex Jenkins. Please.
Hi, thanks very much. Can you see my slides, my cursor?
Yes, we can.
Yes, we can.
Brilliant. So yeah, thank you to the organizers for giving me a chance to talk today. My name's Alex Jenkins. I'm a postdoc at University College London. I'm going to be talking about these two papers, which came out last year. I worked with my collaborator, Diego Blas, who's based in Barcelona. And the concept here is a bit different. So we're looking at ways of detecting gravitational waves, in particular stochastic gravitational waves in the microhertz frequency band, but using binary systems as detectors of these gravitational waves. So rather than being sources of gravitational waves, we want to look at these binaries, measure their orbits very precisely, and see how the orbits respond to the presence of a gravitational wave background. So I'm going to start by talking about stochastic backgrounds in general, although I'm sure that many members of the audience already know a lot about this. And then I'll talk about this binary resonance phenomenon in particular, and then I'll describe our results of this study. So by stochastic background, I mean a signal which looks something like this in the bottom right-hand corner of this diagram. This is just a neat way of thinking about different possible gravitational wave signals you could see. And here we're talking about a signal which is persistent, so it's always on, and it's phase unmodeled, so we don't have like a coherent template we could use to search for it. So in a sense, it's sort of the opposite of the compact binary coalescences that have been detected by LIGO and Virgo so far. And you could get a signal like this essentially from superimposing the gravitational wave emission from many faint or numerous sources which can't be individually resolved. These sources could be astrophysical, like distant compact binaries, or they could be cosmological. You know, you could think about stochastic backgrounds from inflation or from cosmological phase transitions. And that's something I'm going to pick up later in this talk as well. And we characterize these backgrounds in terms of this density parameter. So this is essentially saying how much of the universe's energy budget is taken up by gravitational waves in a given logarithmic frequency bin. So I'm going to show everything in terms of this quantity omega GW rather than in terms of the strain. So in order to motivate why we want to think about these microhertz searches, I want to quickly give a super quick overview of existing constraints on the stochastic background. So we have two key techniques for doing this at the moment. We have ground-based interferometers, such as LIGO and Virgo, and we have pulsar timing arrays. And both of these at the moment rely on looking at how gravitational waves change the flight time of photons. So going to this plot here, I'm showing this omega GW quantity. You can see that on the right, this is the most up-to-date constraints on this from the first 3 observing runs of LIGO and Virgo. And on the left, I'm showing a representative sensitivity curve from one of the pulsar timing arrays. This one is from the Australian Parkes pulsar timing array. So you can see that these are both, very impressive levels of sensitivity. We're measuring, or we're sensitive to parts per billion of the universe's energy density in these two particular frequency bands, but there's a huge gulf in between them at the moment. There are a couple of constraints which exist in between currently. I'm not going to talk about these in detail, but you can see that from a cosmological perspective, they're not particularly interesting because they only tell us that you can't have more than, say, 1% of the universe's energy density in gravitational waves, but that would be pretty enormous in cosmological terms. You can place a better constraint from early universe observations, so essentially from using CMB and Big Bang nucleosynthesis observations to tell us how quickly the universe was expanding at early times, because there's a contribution to that expansion rate which comes from the energy density of gravitational waves. This curve that I've drawn here is a bit different from the others in that it's not frequency specific. this is a constraint on the integral of omega GW over this huge frequency range. So treat this with a bit of caution. And it's also only relevant for, obviously, for gravitational waves which were around at those early times. So gravitational waves coming from coalescing binaries wouldn't be part of this. Okay, so that's the present situation. But if I fast forward to the future, obviously we're all very excited by the science that will be possible with LISA, which is going to sit in this gap between the ground-based interferometers and the pulsar timing arrays. There's also going to be, obviously, updated ground-based interferometers such as Einstein Telescope or Cosmic Explorer. There'll be better pulsar timing arrays, for example, with the square kilometer array. We've heard a bit earlier on about potential interferometers which could sit in the band sort of in between the ground-based interferometers and LISA. And there's also proposals for atom interferometry experiments which would sit in that band as well. But even with all of these exciting new experiments, you can see that there's still a very significant gap here in the microhertz regime. So we're interested in looking at ways of filling this because there could be all kinds of interesting gravitational wave signals waiting for us there. Okay, so the proposal here is to look at the resonant effects of gravitational waves on binary systems. So what I mean by this is you can imagine you have your two objects which are orbiting around each other, and just like any pair of test masses, the proper distance between them oscillates when a gravitational wave comes past. If you try to measure that oscillation directly, that's extremely challenging, but you can have a dynamical effect where if the frequency of the gravitational wave is some integer n divided by the period of the orbit, then you can have this resonance where every time the binary is at the same phase of its orbit, the gravitational wave is having the same force on it. So for example, if it always gets pushed when it's at this point and pulled when it's at this point, and that repeats over many, many orbits, you can have an effect which accumulates and gives you something which is much easier to observe than the kind of direct instantaneous oscillations. So this is why it's very useful to have a stochastic background, which is always on, because it means that you're constantly hitting this system with gravitational waves. And so you are able to accumulate a signal over time. So this idea was not new to us. It's actually something similar is mentioned in the classic textbook by Meisner, Thorne, and Wheeler. And they're very dismissive about this idea, saying that the sensitivity isn't good enough to make it interesting. But this doesn't account for that resonant phenomenon that I was just talking about, which makes the signal much more easily detectable. There were also some, there was a paper by Lamhui et al. Back in 2012, where they looked at this idea and applied it to a particular binary pulsar system. And also some recent ideas were used by my collaborator Diego to look for, rather than gravitational waves, similar effects that can come when you have a coherently oscillating ultralight dark matter field, and how that can have resonant perturbations on binaries as well. So we thought, in light of these more recent developments, we wanted to go away and really calculate what is the most sensitivity gain that you can get from this technique. So the challenging thing with the stochastic background is that you don't know exactly what the strain is doing at any given point in time. It's a random process. And so that means that this randomness propagates into the orbit of the binary. So rather than having a model for how the orbit evolves over time, we need to have a model for how the probability distribution of the orbital elements will change over time. And this is what we do. We're able to evolve this distribution forwards using this equation called the Fokker-Planck equation. This is a well-known tool from many other fields of physics, where essentially we can calculate a diffusion rate and a drift rate in terms of how this distribution evolves, and write this down explicitly in terms of the omega GW, the strength of the gravitational wave background, at each of the resonant frequencies of the binary. So this figure on the left is just an illustration of how, rather than thinking about all of the many, many possible different random trajectories you could take through parameter space, we instead focus on this picture where you think about the probability distribution of all of the possible different outcomes and look at how that changes over time. If you're interested in playing around with this, the code is open source and available on GitHub, and you can evolve your favorite binary forwards in time very quickly and easily. And this is just an example of the output. So each of the little panels here is a figure which is showing, if you think about the covariance matrix between all of the different orbital elements, as the randomness propagates into the orbit, the uncertainty grows. And so typically the values of this covariance matrix gets larger. But you can see that we're able to capture some interesting physics and how they all evolve differently. Some of them grow linearly, some of them grow quadratically because they're sourced by the linear terms. Some of them have this weird oscillatory behavior for this particular system. That's because of the pericenter precession. But all of this is encapsulated in the code that we have developed. Okay, so that's the sort of science of what's going on, but now I want to talk about how we actually apply this and calculate some forecasts for what the sensitivity would be for particular binaries. So there's two probes that we're thinking about in particular. There's timing of binary pulsars, which can give you very precise measurements of the orbits of these systems, and also lunar and satellite laser ranging. So bouncing lasers off of retroreflectors, which were left on the moon, or which are on man-made satellites orbiting around the Earth, which can give you measurements of how far away these things are from the Earth down to the level of millimeters, and so give you a very accurate picture of what the orbits are and what they're doing over time. I think the really nice thing about this is that these data, they already have very exciting and very well-developed science cases, regardless of the stuff that we're talking about today. And so these data will be taken anyway. In a sense, the analyses that we're proposing aren't adding any extra cost. It's just a case of looking at this existing data and analyzing it in a different way to get the gravitational wave constraints for free. So, okay, this is the same figure that I had before, but I've now added the forecast constraints from our method. So there's three different colors here. In red, I have combined constraint from many different binary pulsar systems. In blue, I have the constraint which comes from lunar laser ranging. And in green, I have the constraint which comes from satellite laser ranging with the Lagios satellite. All of the solid curves indicate forecasts for what should be possible with existing data, present day data. Whereas the dashed curves indicate what we expect the sensitivity to be by the end of the 2030s. So roughly, you can think by the time that LISA is coming to the end of its nominal 4-year lifespan. And you can see that in particular with lunar laser ranging, we can get some very interesting cosmologically relevant constraints in pretty much at 1 microhertz. So just to flash up I showed the curve on the previous slide, which came from binary pulsar systems. This figure here is just showing how that comes from combining all of these different constraints from different systems. We went through the ATNF catalog, which contains information about many, hundreds of different binary pulsars, but you can see that the constraints here are driven by just a handful of systems, including at the high frequency end, the Hulse-Taylor system and the double pulsar, these well-known systems. But you can see that going to longer periods and therefore lower frequencies, we typically get stronger constraints. Okay, so here's the same figure again. It's even more crowded now because I've added some signals which might be lurking in this frequency band. I just want to focus on two in particular. So the purple and pink dotted curves, these are to do with the possible signal, the so-called common process signal, which has been detected first by Nanograv and now by all of the main pulsar timing array collaborations. So this is not yet confirmed 100% as a gravitational wave signal. For that, we would need to see the kind of cross correlations between the pulsars that would be indicative of a Hellingsdown correlation. But if it is a gravitational wave signal, you can see that at the sort of steepest spectral indices that are allowed by the Nanograv data, that this would even intersect with the lunar laser ranging constraints that should be possible with present data. If you're more conservative and you fix the spectral index to be that which you would expect from inspiraling massive black hole binaries, you can see that this still intersects with the lunar laser ranging curve for the end of the 2030s. So this could give us some really interesting information about this supermassive binary black hole population. So just one other signal that I want to focus on, I've drawn these two yellow dotted curves here, which are possible signals from cosmological phase transitions. And you can see that these are particularly interesting for us because they're quite strongly peaked. And so with this curve here, I'm kind of showing an example where you can sneak it in between LISA and the pulsar timing arrays. So this is an example of a signal which we could be particularly useful for in setting a constraint in this microhertz gap. So just briefly, these cosmological phase transitions are a generic prediction of very many theories of particle physics beyond the standard model. And I just want to characterize them in terms of these 4 parameters, because on the next slide, I'm going to show you the constraints we can put in this parameter space. So this transition happens at a given temperature, a given epoch in the early universe. There's some strength parameter alpha, which tells you how loud the signal is. There's some rate parameter beta, which tells you basically how many Hubble times it takes for these bubbles to nucleate and collide with each other. And there's a bubble wall velocity, which also affects the strength of the signal. And these peak at a frequency which it's not too difficult to get this frequency to fall in the microhertz band. So here, this is I'm getting very near the end, I promise. This is a diagram showing the parameter space that I was just talking about. And in particular, I want to highlight these blue exclusion regions here, which are those coming from lunar laser ranging. And you can see that there is a region of parameter space which gets eaten out by this, which wouldn't be touched by either LISA or by pulsar timing arrays. So this is just demonstrating a concrete model, a concrete region of parameter space where our methods could tell us something that existing or planned experiments couldn't. So that's it. Thank you very much for listening. I hope I've convinced you that this is an interesting technique that we could use to learn about gravitational waves in the microhertz region. Thanks for listening.
Thank you. Very interesting. Questions, please. Stefano applauds.
So may I also ask a question?
Yes, please.
So when you say you put an upper limit from one of this technique, lunar laser ranging or whatever, you're taking their noise as the limit?
Yeah, so it's a combination of, on the one side, it's our model for, you take a given gravitational wave signal and you compute what is the size of the effect on the orbit that you expect. So how much deviation should we get in the orbital elements? And then you combine that with, from the lunar laser ranging experiments, what their uncertainty is, basically on the ranging distance. And we perform a Fisher analysis to tell us, for a given ranging distance uncertainty, what uncertainty there then is on each of the orbital elements.
And what do you do with the binary pulsar? What do you
with the binary pulsars? It's very similar. So there's a well-known paper by, I'm trying to remember who it is. I think it's Blandford and maybe Damore, I can't remember, but yeah, essentially taking the timing formula for the expected times of arrival of the pulses, which is the your observable, and then you can take derivatives of that with respect to each of the different orbital elements to tell you, yeah, essentially your sensitivity to each of those.
Mm-hmm. Thank you.
Thanks very much.
Thank you. Do we have more questions? No. Then I would like to thank all the speakers in this session, which was a very fruitful and fascinating session, and see you again in a little more than 1 hour for the final plenary. Bye-bye.